welcome to my YouTube channel AV Classes. So today we are going to talk about the modified Ampere's circuit law and Maxwell's equation. So why Maxwell thought that this Ampere's law is inconsistent. So these are the things we are going to discuss in this lecture. So it starts with the basic thing that if a charge is at rest, then it produces electric field. If a charge is moving with uniform velocity, it produces magnetic field. And in same way, whenever the magnetic flux linked with a coil changes, then an EMF induced in that coil, and hence the induced current. So Maxwell used the concept of symmetry between this electricity and magnetism, that whether it is possible that on changing the magnetic field, electric field is produced. So is it possible that if the electric field changes with time, it is possible that magnetic field is produced? So why Maxwell thought such type of things? Let's look at this observation and experiment. It's a parallel plate capacitor which is joined with a battery. This is a key. Now when it is closed, a current I will flow. This is the capacitor C1 and this is capacitor C2. I current will flow. Now, see, this is the parallel plate capacitor. Now, if we are talking about the Ampere's optical law, what it does tells that the line integral of this magnetic field around a closed loop is equal to mu naught times the total current enclosed by that loop. But this is possible for only the conduction current. What does it tells that whenever there is a current, there is a magnetic field. So if we apply this concept here, just draw the Amperian loop here. So this is Amperian loop C1 dash for this C1 and C2 dash for this C2. Now for C1 dash, closed integration B dot dl C1 dash is equal to mu naught I, and closed integration C2 dash B dot dl is equal to 0. Why 0? Because in between these two parallel plate capacitors there is no current. Now in order to make this formula consistent, it has to be valid for each and every point throughout this circuit. So in order to be valid this formula, this both equation must be equal. But how can this be equal? Right hand side is mu naught I and this is 0. So from here Maxwell thought that there is something in between this capacitor which produces some type of current also, and from here concept of displacement current produces. How? Let's see. See, this is the parallel plate capacitor. As the current starts to flow, it starts to charge, due to which an electric field set up in between this capacitor. And what is the formula of that electric field? Let's suppose this is a plane seat. Then electric field produced by a plane seat is equal to sigma upon 2 epsilon naught. Okay. So sigma upon 2 epsilon naught for this plate and sigma upon 2 epsilon naught for this plate, it come out to be sigma upon epsilon naught. Now what is sigma? Surface charge density. Okay. So E is equal to sigma is what? Q by A. Q by A epsilon naught. Okay. Now here see, as the capacitor starts to charge, okay, then it stops charging. Again, the polarity of this voltage changes, due to which it starts to discharge, and hence the electric field that exists in between these two capacitor plate start varying with time. See, this electric field is not uniform. It starts changing with time. So we take the derivative of this electric field to find out how much electric field changes with time. So we find dE by dt is equal to A epsilon naught is constant because area is constant and epsilon naught is the permittivity. So A upon epsilon naught is equal to dQ by dt. Now, what is dQ by dt? Current I. So I is equal to A epsilon naught d by dt. I is equal to this. Take this A in this differentiation. So we get epsilon naught d E A upon dt. So I is equal to epsilon naught d phi E upon dt. Phi is the electric flux. What does it tells that a current is produced in between this capacitor plate, and what is the reason behind it? Due to change in this electric flux, and we call it a displacement current ID. So from here Maxwell thought that is it possible that electric field changes with time produces a current, that is the displacement current. So displacement current is the current which come into existence whenever the electric field or electric flux changes with time. So now this concept Maxwell used to modify this Ampere circuital law and hence give its new equation, that is the line integral of B dot dl is equal to mu naught IC plus ID, where ID is what? Displacement current epsilon naught d phi E upon dt. And this is the concept of displacement current. See, this is the conduction current. Conduction current is throughout this wire. Throughout this wire, IC has some value, but ID is 0. And in between these two capacitor plate, ID has some value and IC is 0. So that this IC plus ID is continuous throughout this circuit, and hence it it is consistent with this Ampere circuital law. So this is all about the Maxwell, their effort to modify this Ampere circuital law. Now let's see, one thing is left, that this displacement current also produces magnetic field. Physicists perform various type of experiment, like putting a compass here, then the needle of that compass deflected, which shows the existence of this displacement current. Okay, now let's look on the Maxwell's equation. So Maxwell combined all the electrostatic equation and magnetism equation, induction equation, to give its 4 Maxwell equation. Let's look at them one by one. First is the Gauss law of electrostatic, that is the line integral of B dot ds is equal to Q upon epsilon. Second one is, this is E. Second one is B dot ds is equal to 0, which shows that divergence of that magnetic field is 0, that is monopole does not exist. Third one is what? E dot dl is equal to minus d phi E upon d, which shows that the change in magnetic flux produces what? Electric field, that is the induced field. And fourth one is the modified Ampere circuital law. E dot dl is equal to mu naught IC plus ID, where ID is what? Epsilon naught d phi E upon. So these are the Maxwell's equation